Now that we know a little bit about how to construct a unit normal vector at any point in a curve, that's what we did in the last video, I want to start exploring an interesting expression. So the expression is the line integral around a closed loop, and we're going to go in the positive counterclockwise orientation, of a vector field f dotted with the unit normal vector at any point on that curve ds. I'll write ds in magenta. ds. So first let's conceptualize what this is even saying, and then let's manipulate it a little bit to see if we can come up with an interesting conclusion. We actually will manipulate it. We'll use Green's theorem, and we're going to actually come up with a two-dimensional version of the divergence theorem, which all sounds very complicated, but hopefully we can get a little bit of an intuition for it as to why it is actually a little bit of common sense. So first let's just think about this. So let me draw a coordinate plane here. So we do it in white. So this right over here, that's our y-axis. That over there is our x-axis. Let me draw ourselves my curve. So my curve might look something like, I'll do it in the blue color. So my curve might look something like this, my contour, and it's going in the positive counterclockwise direction just like that. And now we have our vector field. And just as a reminder, we've seen this multiple times. My vector field will associate a vector with any point on the xy plane, and it can be defined as some function of x and y. I'll call that p. Some function of x and y times the I unit vector, so it says what the I component of the vector field is for any x and y point, and then what the j component, or what we multiply the j component by, or the vertical component by, for any x and y point. So some function of x and y times I plus some other scalar function of x and y times j. And so if you give me any point, there will be an associated vector with it. Any point, there's an associated vector, depending on how we define this function. But this expression right over here, we're taking a line integral. We care specifically about the points along this curve, along this contour right over here. And so let's think about what this piece right over here is actually telling us before we sum up all of these infinitesimally small pieces. So if we just take f dot n, so let's just think about a point on this curve. So a point on this curve, maybe this point right over here. So associated with that point, there is a vector. That's what the vector field does. So f might look something like that right over there. So that might be f at that point. And then we're going to dot it with the unit normal vector at that point. So the unit normal vector might look something like that. That would be n hat at that point. This is the vector field at that point. When you take the dot product, you get a scalar quantity. You essentially just get a number, and you might remember, and there's several videos where we go into detail about this, but that tells you how much those two vectors go together. It's essentially, if they're completely orthogonal to each other, you're going to get 0, and if they go completely in the same direction, it's essentially you're just going to multiply their magnitudes times each other. And since you have a unit normal vector here, what this is essentially going to give you is the magnitude of the vector field f that goes in the normal direction. So think of it this way. So let's think about the component of this that goes in the normal direction. It might look something like that. This would be the component that goes in the tangential direction. So this expression right over here is going to give us the magnitude of this vector. Let me write this down. This right over here is the magnitude of the component of f in the normal direction, or in the same direction as that unit normal vector, normal direction. And then we're going to multiply that times a very infinitely small length of our contour, of our curve right around that point. So we're going to multiply that thing times this right over here. And so you might say, well, okay, I kind of get what that is saying, but how could this ever be physically relevant? Or what could be the intuition for what this expression is even measuring? And to think about that, I always visualize, this is in 2 dimensions, you will later do things like this in 3 dimensions. Imagine this is a 2-dimensional universe, and we're studying gases. And so you have all these gas particles in a 2-dimensional universe, so they only can have kind of an x and y coordinate. And this vector field is essentially telling you the velocity at any point there. So this is the velocity of the particles at this point. This is the velocity of the particles at that point. That is the velocity of the particles at that point. And so when you take f right on this curve, that's the velocity of the particles at that point. They're going in that direction. When you dot it with n, it tells you essentially the speed going straight out right at that point. And then when you multiply that times ds, you're essentially saying what at any given moment, how fast, or at any given at that point right over there in the curve, how fast are the particles exiting the curve? And so if you were to sum up all of them, which is essentially what this integral is doing with this line integral, it's essentially saying how fast are the particles exiting this contour? Are they, or even entering the contour if you get a negative number? But since we're taking the unit vector that goes, the unit normal vector that is outward pointing, it's saying how fast are they exiting this thing? If you got a negative number, that means there might be some net entrance. So this whole expression is, if you take that analogy, it doesn't have to have that physical representation. How fast are particles, are 2-dimensional gas particles exiting the contour? And in the future, we can do it in 3 dimensions where you have a surface, and you can say how fast are things exiting that surface. And so let's start, now that we have hopefully a decent conceptual understanding of what this could represent, let's play around with it a little bit, especially because we know how to define a normal vector. So let's rewrite it using what we know about how to construct a normal vector. So if we rewrite it, our integral becomes this. We have our vector field f, dotted with the normal vector. The normal vector we can write this way. A normal vector we saw was dy times I minus dx times j, and then we had to divide it by its magnitude in order to make it a unit normal vector. The magnitude was this right over here, dx squared plus dy squared, which is the same thing as ds, which is the exact same thing as that little mini arc length, that infinitely small length of our contour. So we're going to divide it by ds. And then we're going to multiply it times ds. And ds is just a scalar quantity, and so we can actually even multiply this thing times ds before taking the dot product, or vice versa. But these two things are going to cancel out. And so we're essentially left with f dot this thing right over here. But we have f defined right over here, so let's take the dot product. So I'll just write the integral, the line integral symbol again. We're going in the counterclockwise direction. And when we evaluate, and now let me pick a color that I have not used. I've used so many colors. So I'll do yellow again. So now let's evaluate f dot this business. So dot product, fairly straightforward. You take the product of the x components, or essentially the scalar component, the magnitude of the x components. So it's going to be p of xy times dy. So it's going to be p of xy times dy, and then plus the product of the magnitudes of the y component, of the j components. So it's going to be plus q of xy times minus dx, so times negative dx. Well, that's going to give us negative q of xy times dx. So this is kind of an interesting statement. We've seen something like not too different than this before, when we saw even just the definition of Green's theorem. Let me rewrite it here just so we remember. So the definition, when we learned about Green's theorem, it told us if we're taking a line integral over this contour, and there's multiple ways to write it, but one way that we often see it, and we've explored it already in our videos, is if we were to say we have m times dx plus n times dy, this is equal to, and I'm just restating Green's theorem right over here, this is equal to the double integral over the region that this contour surrounds of, and you whatever function you have here times dy, you take the partial of that with respect to x. So you take the partial of this with respect to x, the partial of n with respect to x, and from that you subtract whatever was on the dx side, so the partial of m with respect to y, and then you could say times dx dy, or you could say dA for the infinitesimally small little chunk of area. So I'll just write, I could write d. Let me write dA here. Alright, dx dy, or it could be dy dx. Actually, let me just write dA here, so since we're speaking in generalizations, where dA is an infinitely small little chunk of area. So this right over here, this is just a restatement of Green's theorem. So we already know this. This is a restatement of Green's theorem, and how can we apply it here? Well, it's the same thing. We have a little bit of sign differences, but we can apply Green's theorem right over here. This is going to be equal to the double integral over the region that this contour surrounds. And then what we want to do is we want to look at whatever is the function that's being multiplied times the dy. And in this case, this is the function that's being multiplied times the dy. And we want to take the partial of that with respect to x. We're going to take the partial of p with respect to x. So the partial of p with respect to x. And then from that, we are going to subtract. We're going to subtract the other function, whatever is being multiplied times dx. We're going to take the partial of that with respect to y. So here, we're going to take the partial of this whole thing with respect to y, but we have a negative out here. So it's going to be minus partial of q with respect to y, and then we have dA. And obviously, these two negatives, and subtracting a negative just gives you a positive. So then this is going to be equal to the double integral over the region, and maybe you might already see where this is going, maybe getting a little bit excited. The partial of p with respect to x plus the partial of q with respect to y, dA. Now, okay, I took the partial of, okay, what is this telling me, Sal? Well, look at this thing right over here. P was originally the function that is telling us kind of the magnitude in the x direction. Q was telling us the magnitude in the y direction. We're taking the partial of this with respect to x. We're taking the partial of this with respect to y, and we're summing them. This is essentially, or this is exactly, the divergence of f. And if that doesn't make any sense, go watch the video on divergence. This right over here is the divergence of f. This is the divergence, by definition really, this is the divergence of our vector field f. And so we have a very interesting thing. This thing that we saw, this original expression that we started studying, which is essentially saying what's the speed at which the particles are exiting this surface. We now get it in terms of this little expression, and we'll interpret it in an intuitive way in a little bit. So this is equal to the divergence of f times dA over the whole region. So the double integral. So we're summing up the divergences of f times the infinitely small little chunk of area, and we're summing them up over the whole region. Now, why does that make intuitive sense? And for you to realize why it makes intuitive sense, you just have to remind yourself what the divergence is. Divergence is a measure of how far, of whether things are expanding or diverging or kind of contracting. If you have a point over here, where around that the particles are kind of moving away from each other, you would have a positive divergence here. If you have a point, sometimes called a sink, where all of the particles are kind of condensing or converging, you would have a negative divergence here. And now, so this should make a lot of sense. You take any little infinitely small area in this, and then you multiply that times the divergence there. So the more divergence here, you're going to get a larger number. And then you sum them up across the entire region. And so that makes a lot of sense. The more diverging that's going on through your region, obviously the more stuff is going to be exiting your boundary over here. So it actually makes complete sense, or hopefully it makes a little bit of complete sense. Why, if you were to see how fast are things exiting the surface, it's really the two-dimensional flux. How fast are things exiting the surface, and you take the sum over all of them, that's going to be the same thing as summing all of the divergences over this area that the contour is surrounding. So hopefully that makes a little bit of sense to you, and it's actually another way of kind of thinking about Green's theorem. And we also have just explored what we've just said, this expression, that the divergence summed over this region over here is the same thing as the f dot n over the contour. That essentially is the two-dimensional divergence theorem.